Welcome to Chapter 12, Distributed Database Management Systems. The primary difference between a NoSQL and SQL database is SQL or relational databases have characteristics that can be summarized with the acronym ACID, and we'll be going over that in this lecture. In contrast, NoSQL databases have characteristics that are summarized with the acronym BASE. And again, we'll go over what that stands for a little bit later in this lecture after we've laid some groundwork. Understanding the difference in database philosophy of the use between ACID databases and BASE databases will give you a fundamental understanding of NoSQL databases and why they're important in today's world. So the learning objectives for this chapter are we're going to learn about distributed database management systems, how transactions are managed in a distributed database environment with something like a two-phase commit or a quorum two-phase commit. Also, how distributed database design draws on data partitioning and replication to balance performance. So you may have heard that NoSQL databases do not have schemas. While it's not mandatory to have a schema in NoSQL, having a logical schema avoids certain problems. First, we need to organize data regardless of the physical database implementation. A schema provides a roadmap of our data. It lets us pay attention early on to data types, and we can use the collections, which in a NoSQL document database are the equivalent of tables. We can use those type of organizational constructs like collections to our advantage. So a distributed database consists of loosely coupled sites that share no physical components. Database systems that run on each site are independent of each other. Reads and updates may access data at one or more sites. And this is in contrast to a centralized database management system where all the data and the processing power resides on a central site, and then access at remote locations is provided through dumb terminals. And here's a graphic of the centralized database system. This was highly characteristic of the mainframe era. You had a very powerful mainframe computer that hosted the database management system. Requests were sent to it from terminals by remote users. So NoSQL databases arose because of the limitations inherent in the ACID properties of relational databases. With the advent of e-commerce, the number of concurrent users for database systems climbed from tens of thousands to millions. And think of Twitter, which originally was hosted on a relational database system. It was always crashing. Then they went to a NoSQL, a distributed technology, and they were able to maintain their uptime and availability without those embarrassing pictures of a whale being carted away by a bunch of pigeons. So the way this is done is in terms of the consistency of the replicas. You can distribute your processing load amongst many replicas of your database. and that's what NoSQL databases do. Relational databases can do that for reads, but for updates, they run into a problem. And that is, with a relational database system, you have the need for immediate consistency. In other words, when you make a change on a server in the East Coast, let's say Washington, D.C., it must be reflected immediately on a server on the West Coast, let's say Redmond, Washington. So that immediacy means that you have to do a couple of things. When a potential update is being made to a database in, let's say, the one in Washington, D.C., you have to query the server in Washington to find out if it's available to make the same update. If it isn't, then you have to go through the whole process again. If it is, then you'll send the transaction and you'll give it a go signal, go and do the update. Then you have to check to see if the update was made. If it wasn't, then you have to roll back the update in Washington, D.C. So this is known as a two-phase commit. And it's necessary, a two-phase commit like that is necessary if we want to have immediate consistency. And you can imagine what it would be like if we had 50 database servers we were distributing our load on. NoSQL databases do not have that requirement for immediate consistency. So with a NoSQL database server, in the same scenario, you would make your change in Washington, D.C. It wouldn't have to immediately be reflected in Redmond, Washington. You have what's known as eventual consistency. Eventually that change will be made in Redmond, Washington, but there's no compelling reason to make it right this instant. There's still use cases for the immediate consistency of relational databases. Imagine if you're going to be registering for classes. You have a couple of servers, and the one you go to, you're a graduating senior this semester, you need 3 computer science classes, and they're filling up rapidly. So the server you go to, you log in and you get 3 computer science classes, so you're happy, looks like you're going to graduate on time. And if this is NoSQL database technology, here's what could happen. You end up going to class, and you find out that you actually didn't get one of the 3 classes you thought you did, because someone else at another server got it before you, and it wasn't reflected on your server until half hour to an hour later, and so you missed out. So there are still use cases for the ACID properties of relational databases. But with the globalization of commerce through e-commerce, we've had to also look at distributing the load and then relaxing the immediate consistency on many different types of systems. So again, not only the internet, but also mobile wireless applications are making updates to our systems as well. So there's an underlying principle in relational databases that makes them very suitable for use cases in certain situations, but it limits their scalability. Some information systems require that a database take extraordinary measures to protect data integrity and reduce data anomalies. Use cases here might be things like bank accounts and class registration. So again, you have to look at the use case to decide if you really need a SQL database with its ACID properties, or if you can look at the use of a distributed database system, commonly known as NoSQL database systems where you have eventual consistency. Don't get me wrong, SQL databases or relational databases can be distributed, but they're mostly distributed for read operations. You run into scalability problems when you try to scale them and allow updates at all locations, as I just went through. And here's some advantages and disadvantages of distributed databases. Obviously, they're going to be more complex. They're more technologically sophisticated. That's a disadvantage. Security, you're going to be concerned about what's going across the wires. There aren't distributed database standards like there are for the SQL databases. On the other hand, some of the advantages is it improves communications. Data is going to be located where the biggest demands are, so it doesn't have to go across the world to get the data. It can be right there. And there's less danger of a single point of failure. So with a distributed database, there can be a couple of different types. You can have a homogeneous distributed database, and here all sites have identical software. On the other hand, with a heterogeneous database system, and that's the goal these days, different sites may use different hardware and software. And some of the main characteristics of a database management system that's distributed is the transaction management is different than it would be on a relational database. And you also have a mapping function that's going to take your query and then find out where the data resides on all the various replicas you have around the world, and then map a query to go get the data from those replicas. But it still has many of the same things: query optimization, backup and recovery, concurrency control, and so on. In most of the major database vendors, MongoDB has stated this, and they're the leading NoSQL database vendor. They built on the work that was done on relational databases. There was no reason to throw out the 40 years of work doing very sophisticated algorithms that proved effective and are battle tested in relational. Why throw them out? Reuse them in NoSQL. So here we have a fully distributed management system. So you have fragments of your database on two different systems, and you have users in a network, communication network, could be around the world, that are going to be accessing the data and updating the data. You can also have it distributed processing, where you actually have multiple machines working on the same problem using a distributed database. So some of the components that we have in a database management system are the transaction processor. Remember in our example of two databases, one in Redmond, Washington, one in Washington, D.C., we had a need for some function to ask the server in Redmond if it was ready to receive an update when one was made in Washington, D.C. Well, that functionality is known as the transaction processor or transaction manager or transaction monitor. And it's going to be coordinating the transactions between the replicas of the database. So one of the options for databases is the centralized approach, where processing is done on a single host computer and data is stored on a single host computer. And then the users access the database through, in effect, dumb terminals. Here's a graphic of exactly that situation. You can have a front-end processor, and this goes back to the IBM days. They had front-end processors to handle the communications so that the mainframe could focus on the actual important transactions. So your front-end processor takes the dumb terminal requests and forwards them to the database management system. Next came the client-server architecture, and that spread some of the load onto the clients. Once we had PCs, we had desktop clients that could handle processing. They had memory, and they had a disk, and they had CPU. And so here we had a variety of different PCs accessing the database. And we've gone over the multi-site or distributed database system. And we have the homogeneous, heterogeneous, and then fully heterogeneous. That supports different database management systems, each supporting different data models. So we can really put our database distributed on low-cost commodity hardware, and we can scale really high as a result of that. So we have a set of restrictions for a distributed database management system. You can have a restriction such as the number of remote tables that may be accessed in a single transaction, the number of distinct databases that can be accessed, things of that nature. And it depends on how you test your system, and the performance results that you get will decide what type of policies like this you put in place, and then your programmers would enforce that in the code. So here we have some transparency features of databases. Data transparency is the degree to which the system user may remain unaware of the details of how and where data items are stored in a distributed system. So we can consider transparency issues in relation to fragmentation, replication, and location transparency. So distribution transparency allows management of physically dispersed databases as if it was centralized. And again, we have those three levels: fragmentation transparency, location transparency, and local mapping transparency. So replication, we've been using this term a little bit. The system maintains multiple copies of all the data stored in different sites, which gives fault tolerance. If one site goes down, you've got the data in other sites. And it also gives faster retrieval, for a worldwide database system if you have local servers. A fragmentation or sharding is a little different from replication. Here our data is partitioned into several fragments, and those fragments can be replicated to multiple sites. And then replication and sharding can be combined together. Data is partitioned into several fragments, and the system maintains several identical replicas for each fragment. Some of the advantages of replication: availability. Failure of a site containing a data set does not result in unavailability if replicas exist. Another advantage is parallelism. Queries on a data set may be processed by several different nodes in parallel. And a third advantage is reduced data transfer. Again, if it's located locally and not across the world, it's going to be much less communication latency. Some of the disadvantages of replication: increased cost of updates. Each replica of a data set must be updated across all the replicas you have. Increased complexity of concurrency control. Concurrent updates to distinct replicas may lead to inconsistent data unless special concurrency control mechanisms are implemented. One solution is to choose one copy as the primary copy and apply concurrency control operations on the primary copy. We also have been talking about fragments, and there's two types, and we mentioned them, horizontal and vertical. Let's go over the advantages of each. Horizontal fragmentation allows parallel processing on fragments of a data set. And it allows a relation to be split so that the rows are located where they're most frequently used. So with horizontal, you're taking complete rows, but you're separating the table by some parameter, let's say geographic location. So you're taking all of the complete rows for the West Coast and you're putting it in Redmond, Washington. You're taking all of the complete rows for the East Coast and you're putting them in Washington, D.C. That's an example of a horizontal fragmentation. A vertical fragmentation is where you split the columns. So you take all the rows, but you only take the first 4 or 5 columns and you put that in Redmond. You take the 6 through the last columns and you put that in Washington, D.C. A vertical allows rows to be split so that each part of a row is stored where it's most frequently accessed. The row ID attribute allows for efficient combining of the vertical fragments. And it also allows processing on a complete data set. So transaction transparency. Transactions will maintain the distributed database's integrity and consistency. And the mechanism for that is through a transaction coordinator and a transaction manager. A transaction coordinator controls updates between different replicas. Transaction manager handles an update on one machine. So if you have a request to update a record on Washington, D.C. server, it'll go to the transaction manager. That'll toss it up to the transaction coordinator. Transaction coordinator will talk with the transaction manager in Redmond. Doesn't go to the coordinator in Redmond, it goes to the transaction manager and says, are you ready for an update on this table and row? And then it coordinates it. When it gets an affirmative from both locations that they're ready to go, then it'll do an immediate update for those things. Now, that's with an immediate consistency. With an eventual consistency, the update will be made to the Washington, D.C. computer, and the transaction coordinator will use one of a variety of distributed update methodologies to eventually get the transaction manager in Redmond to update the data. And here we see a couple of different types of transaction classification: remote request, distributed request, and remote and distributed transactions. Concurrency control, again, is important in distributed database environments. And here is an example of how a commit is going to be done between 3 different sites. So I was The example I was giving was between two sites. But when you start getting into more sites, then you have some other options. You can do what's known as a quorum two-phase commit. So in this case, the transaction coordinator would be happy if it had a majority of the sites that are ready to update, and they do the update immediately, and then the other sites will update as they get the opportunity. And then it can use timestamps, or it can have a case where you have to read at least a majority of the sites, which is half plus one, in order to, and then find the most current values in order to get to use a value. So that's a quorum two-phase commit, is a technique for using distributed databases. It lets you maintain, depending on how you slide the bar for how many you demand to be updated at once, it'll let you maintain immediate consistency, or you can have it so that you don't read enough, you don't update enough replicas with the reads that you're requiring to ensure that they have the most up-to-date data, but it's still going to be advantageous in that you've got a majority, well, you've got a large number of sites updated. You only have to worry about the eventual consistency on the other sites. So two-phase commit, we've gone through this. You ask, a transaction is done at one location. Transaction coordinator asks all the replicas, are they ready to do an update? They will all send back a yes, and if that's the case, then it'll send out a message, update. If one of them comes back, hey, I had a problem, then roll back. On the other hand, you could have the transaction coordinator send out, you get an update in Washington, the transaction coordinator asks all the other replicas, are you ready? One of them may say, no, I'm not ready just yet. So you might even get stymied even at that first point. But eventually, if you keep trying and trying and trying, depending on how many, if you've got like 50 servers worldwide, that's going to be a lot of times you have to retry in order to find a case where all of them are ready at that instant to make an update to a table and a record in that table. So eventually they'll all say yes, you'll give the commit, and none of them will have a problem, and then you're good to go. You can see how that can be very lengthy and how that limited the scalability of the ACID-based SQL relational databases. And we have performance transparency that allows this distributed database to perform as if it were a centralized database. Now, there's going to be some problems with performance transparency in the sense, like, let's say what we're doing is Facebook, and we have the one server on the East Coast, Washington, D.C., the server on the West Coast is Redmond. I make a change to my page in Washington, D.C., and we don't have immediate consistency. Well, it may be a couple hours or longer before my page in Redmond is updated. Not a big loss, but it's not complete performance transparency. So you have, with distributed databases, network latency, which is a delay that is caused by the amount of time it takes to traverse the network. And you also have network partitioning. And if nodes become unavailable because of some minor network failure, then you're going to add that problem as well. So partitioning is when a network is decomposed into multiple parts because of a communication failure. With distributed data, we need to decide how to fragment our data, vertical or horizontal. Do we have a whole database, or do we fragment it into parts, I guess is the first thing we need to ask. And then once we fragmented it, if we do need to fragment it, how do we replicate it? All the parts at each location, or some parts go to some locations, other parts go to other locations. And where do we locate it? So, we've got a worldwide audience. How do we minimize our communication delays? So that where to locate, that's a data analysis optimization problem, as those of you in my data analytics class are aware. So again, fragmentation can be horizontal. You divide the relation into subsets of rows, and those subsets are known as fragments. Vertical fragmentation, you divide the table or relation into columns. And of course, you can get a combination of the two. So if we assume our individual resources are unreliable, then in this case, to provide high availability, we have to replicate our data partitions. New nodes can be added to the replication, and when one joins, it can either broadcast its presence to all the nodes or notify some well-known nodes. With multiple copies of our database, we need to synchronize them so users have a consistent view of the data. And we have several different consistency models: a strong consistency, eventual consistency, and that can be different technologies: read your write consistency, session consistency, monatomic read consistency, and so on. Now, a two-phase commit on a single master configuration, a change in the master in a two-phase commit on is then results in a change in each replica. However, the changes are only allowed on a single master. On a multi-master configuration, changes are allowed on multiple masters, and a change in any one of them results in a two-phase commit on each replica and on the other master or master controllers. A two-phase commit provides strict consistency. So transactions need to access the data at multiple sites. In other words, you make a transaction, an update in Washington has to be updated in both Washington and Redmond at the same time. To assist with the two-phase commit, each site has a local transaction manager and a transaction coordinator. And then a centralized data allocation, entire database on one site, partitioned, database is divided, and the fragments are stored at two or more sites. And replicated is copies of one or more database fragments or stored at different sites. So if you've got one of your replicas with a fragment, let's call it fragment A, goes down. If you have another replica with fragment A, you're still in business. So what is consistency? Strong consistency are read and write operations on a replicated object are done at each replica set at the same time. Weak consistency is read and write operations on a replicated object are eventually reflected in the other members of a replica set. So that's consistency in the CAP theorem. Availability, for distributed systems, availability of a system to process requests for a large system at almost any point in time, there's going to be a chance that a node goes down. So many applications require continued operations even at the cost of consistency. So you have these multiple replicas. You may not be able to keep them all immediately consistent, but you've got multiple copies of them. So if Washington, D.C. server goes down, you can transfer your traffic to Redmond server and it can handle them. It may not have had the most recent information. So again, there's no free lunch. You've got trade-offs for everything. So the CAP theorem is also known as Brewer's CAP theorem. And there's three properties of the system. Consistency, all copies have the same value. Immediate, you make a change anywhere, it's immediately that they all have the same value. Eventual is you make a change somewhere, eventually it'll get around to updating it in all the other places. Availability is that the system can run even if parts have failed. And partitions are the network can break into two or more parts, and each with active systems that can't talk to the other parts, but you can still operate in those separate parts. You know, if you have a PC in part A of the separation, it can work in part A, likewise part B, and then you have to reconcile changes made afterwards. So that gets back into this eventual consistency. So Brewer's CAP theorem is you can have at most two of these three properties in any large system. So for very large systems, they'll partition at some point in time. So you choose one of consistency or availability. Traditional databases choose, and that means the relational databases, they chose consistency. And most of the web applications that need, high volume, they choose availability. So we have acid properties and base properties. Acid means atomicity, either all actions are carried out or none are. Consistency in the terms, in the context of distributed databases is immediately a change is made across all replicas. So all replicas always have exactly the same data. Isolation, transactions are isolated or protected from each other, and of course durability, transactions that complete are going to be permanent. We also have base properties, and base stands for BA stands for basically available. System always available. E, with a caveat, some subsets of data may be unavailable for short periods of time. The S in base stands for soft state. Soft state means the system will be changing even without updates to the data, as distributed modifications are reconciled and applied throughout. So in other words, we've got a backlog of updates that need to be distributed among all our replicas. Even if we stop doing updates, that backlog of updates that haven't been distributed would still result in database updates throughout the system for a period of time. The E stands for eventually consistent. And the guarantee is that at some point in time in the future, the data will become consistent in all the different replicas that the users are interfacing with. Until then, you may see different values for the same record in different locations. So we see in this chart the spectrum from the centralized relational two-phase commit to the modern NoSQL databases. And you can see that the main difference is that the two-phase commit in the relational distributed databases sacrifices availability to ensure consistency. And on the other hand, the NoSQL sacrifices consistency to ensure availability. So again, there's no free lunch. You're going to have to choose one or the other. So a distributed file system stores data across a large collection of machines, but it provides a single file system view. A highly scalable distributed file system for large data-intensive applications may have 10,000 different nodes, 100 million files, and 10 petabytes of data. It's going to provide redundant storage for massive amounts of data on cheap and unreliable computers. Files are replicated to handle hardware failure. It detects failures and then recovers from them. And there's a couple of examples. Google File System is one, and Hadoop File System is another. So with Hadoop, you've got a single namespace for the entire cluster. Files are broken up into blocks. Your typical block size in Hadoop is going to be 64 megabytes. Each block is replicated on multiple data nodes. The clients are going to find locations of blocks from the name node, and the client will access the data directly from the name node. The name node maps a file name to a list of block IDs. It matches each block ID to data nodes containing a replica of the block. The data node maps a block ID to a physical location on the disk. So you can see how we get all the way down to the location on a disk on one of these cheap hardware platforms that we've distributed things to. Data coherency, write once, read many, is the access model, and the client can only append to existing files. Distributed file systems are good for millions of large files, but they have very high overheads, and billions of smaller rows lead to very poor performance. Now that's not the case with some newer advances. We have Spark as a big data platform, and it is going to address, and it does address, many of these problems. It's about 100 times faster than Hadoop distributed file system. And it gives you access to a wide variety of well-known data types like various database systems and things like text files, CSV files, Parquet files for Hadoop, and so on. But Hadoop is kind of the granddaddy of distributed file systems, but it's being supplanted now by Spark. Okay, this concludes our lecture for Chapter 12. Thank you.